hopefully won't have a bunch of it's okay, but could be better. So now we are on chapter 1 of Introduction to Cybernetics. This is chapter 1, the abstract theory of algorithms. Now, like I said before, I'm just going to read the English. I'm not going to really uh, get super focused on the different formulas and things. I'm just going to concentrate on the English because uh, I want to keep this moving. So if you want to go, I will look at the formulas, each one, so you can focus on them if you want. Just pause the video on that. But like I said, I want to keep this going. So okay, so alphabetic operators and algorithms. Sorry, it just jittered out. Sorry. Okay, an abstract alphabet is any finite set of objects called the letters of the alphabet. The nature of these objects is, for our purposes, immaterial. The letters of abstract alphabets can be, for example, letters of the alphabet in any language, Latin, Greek, Russian, etc., digits, any signs, diagrams, and so on. If necessary, abstract alphabets can be introduced where the letters are complete words from some natural language, for example, English. The only important requirement of an alphabet is that it be finite, i.e., that it consists of a finite number or of letters. Let me read that again. The only important requirement of an alphabet is that it be finite, i.e., that it consists of a finite number of letters. Having introduced the concept of the abstract alphabet, we define a word in this alphabet as any finite ordered sequence of letters. For example, in the alphabet, A equals A X Y. I'm probably not saying that right. Consisting of the two letters X and Y. Words will be in any sequence such as X, Y, XX, XY, YX, YY, triple X. The number of letters in a word is usually called the length of the word, so that the words in this example have lengths 1, 1, 2, 2, 2, 2, 3. In addition to the words of a positive length consisting of at least one letter, it is often useful also to consider empty words, words that do not contain any letters. In this book, an empty word will be denote. Are we back? Okay. Sorry, we're going to do that again in case that time. In addition to words of a positive length consisting of at least one letter, it is often useful to consider empty words, words that do not contain any letters. In this book, an empty word will be denoted by the letter E for empty, I guess. Sometimes, however, it is convenient to denote an empty word in complete agreement with its definition by not using any letter in the place corresponding to the empty word. We note that by this definition of a word, the concept of a word in the Latin alphabet differs from the concept of a word adopted in natural languages. By our definition, words can consist of any combination of letters, including meaningless combinations. Thus, the letter as algorithm, mathematics, BKLT, and DDDD must be regarded as words in the Latin alphabet, considered here as an abstract alphabet. When an alphabet is enlarged, i.e., when the new letters are incorporated into it. The concept of a word may undergo substantial changes. If, for example, we enlarge the Latin alphabet by the letters letters with nothing in them. what quotation marks and comma? What is going on here? And the above listed four words in the Latin alphabet can be considered as a single word in the enlarged alphabet. By adding to the Latin alphabet the punctuation signs and a separator, an empty space between neighboring words, we can, if necessary, consider whole sentences, paragraphs, or even complete books as individual words. What is this? In the same way, the expression 69 plus 72, consisting of two words, 69 and 72, in an alphabet, A, for alphabet, I guess, of 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, connected by the addition sign, can be regarded as one word in an enlarged alphabet, A, which is obtained if we add to it the new letter plus the plus sign. An alphabetic operator or an alphabetic mapping is any correspondence function that places words in some alphabet into correspondence with the words in the same alphabet or in some other fixed alphabet. The first alphabet is called the input alphabet, and the second the output alphabet of the given operator. When the input operator is specified in the corresponding alphabet. I've never seen such word strings before. Subsequent discussion will deal basically with single-valued alphabetic operators which assign to each input word a word in the input alphabet of the operator, not more than one output word, a word in the same alphabet of the operator. If the alphabetic operator does not assign to a given input word P any output word, not even an empty one, then we shall say that it is undefined for this word. The set of all words for which an alphabetic operator is defined is called its region of definition. Region of definition. That might make a good little rap. On this basis, by the term alphabetic operator, we shall always mean, unless otherwise stated, a single-valued, partially defined, generally speaking, mapping of a set of words in the input alphabet of the operator into a set of words in its output alphabet. Because it is possible to specify alphabetic operators for sub sets of words, we can, without loss of generality, always assume that the input and output alphabets of the operator are identical. In order to do this, it is sufficient to combine the input and output alphabets of a given operator. What is that? Yeah. I'm not familiar with my Greek. Into one general alphabet A, and to specified for only those words that occurred in the original region of definition of the operator, whatever that doodad is. Each alphabetic operator is associated with an intuitive representation of its complexity. The simplest operators are those that accomplish letter-to-letter mappings. In letter-to-letter mappings, each letter X of the input word P is replaced by some letter Y of the output alphabet, depending only on the letter X, but not on the choice of the input word P. Letter-to-letter mappings are completely defined by a specification of the correspondences between letters of the input and output alphabets. In our later exposition of so-called code mappings, which we shall call codings for brevity, will be of great importance. In the simplest case, words of one alphabet, say in alphabet A, are coded by words in another alphabet B as follows. Each letter A, lowercase a, of the alphabet uppercase A is assigned some finite sequence B. What? I can't read this. Of letters in alphabet uppercase B is called a code of the corresponding letter in such a way that the different letters of alphabet uppercase A are assigned different codes. To construct the required code mapping, it is now sufficient to replace all letters of any word lowercase p in alphabet uppercase A by their corresponding codes. The word obtained in this way in alphabet uppercase B is called the code of the original word lowercase p. We shall agree that the code mappings must always be reversible. In other words, different words in alphabet A must have different codes. The condition of the reversibility of coding is the same as the condition of that the corresponding code mapping must be a one-to-one mapping. I'm getting wrecked. It is easily seen that the reversibility of coding is not ensured by the single condition that the codes of different letters, words of length 1, should be different. Indeed, if the letter that is assigned, okay, we're back, okay, and the letter that where I'm pointing right there, the code this one, then the code BBB will be obviously correspond. Obviously, that's the wrong word to use here. Correspond to both this and also to words that one and this one. It is easy to verify the fact that a coding will be reversible whenever the following two conditions are satisfied. The codes of different letters of the initial alphabet are different. The code of any letter of alphabet uppercase A cannot be identical to any initial section of codes of other letters of this alphabet. In fact, let's assume that both of these conditions are satisfied and let the word, okay, look at that one. Whoa. Be the code of some word. Uh-oh. It's getting thick. In alphabet uppercase A. We show that from the code lowercase q, we can unambiguously restore the word lowercase p. Because of condition B in only one initial section of word lowercase q could coincide with the code of some letter of alphabet A, uppercase A. It is clear that such a section is the code of letter da. Upon deleting this section, we obtain the code that of word this and that and. Applying the same considerations we. Oh, and by the way, the word lowercase p is called the initial section of the word lowercase q. If the word this is that different. Lowercase q has a form q equals pr, where r is any word possibly empty. How far is this? How much does this go? This is killing me. Oops. It's killing my audience too. Bro. So, is there a stopping point anywhere? Oh, man. So I'm going to stop at page 4 right here. It's getting too hard on me to keep going. I mean, they're throwing all these empty words and weird things at me. It's just driving me crazy. Okay, so we're going to cut off on page 4 and we'll continue next time, okay? All right. Thank you very much for tuning in.